Hello everybody. In this video, we'll learn about double integrals over non-rectangular bases. So previously, we learned how to calculate double integrals. It's like calculating a single variable integral twice. And for example, maybe we want to find the volume underneath this surface, right? This blue mountain-like surface, as usual. Z is a function of x and y. The volume under this surface that lies over this rectangular region in the xy plane. So here x varies from a to b, and y varies from c to d. Right? The values of x that are in between these two bounds, and the values of y that are in between those two bounds, right? That defines this region in between both. Right? This set of points satisfies both these inequalities. And that leads us to calculate a double integral which has this form. And just to recap what we talked about in the last lesson, right, we always respect the order of parentheses. We calculate the inner integral first. Right? We have d in some variable. In this case, we have dy, so we'll treat y as the variable and x as a constant. When calculating this, we'll calculate the antiderivative. Then plug in the values y equals d minus y equals c. The result will be a function of x, and then you can integrate that function of x. Now the goal is going to be to look at different shapes of bases rather than just rectangles. To take a look at this three-dimensional graph from a different point of view, imagine that you were on top of the z-axis and looking straight down at the xy plane. So this diagram over here represents what you might see. Right, the x-axis, right, that's varying from a to b. Right, so that corresponds to this. And on the y-axis, we vary from c to d. So that corresponds to this region. And the way the double integral is set up, for each value of x, right, the y values range between c and d. And so for this value of x, for that value of x, and then that covers the entire rectangle. But what if we want a different shape? Probably the next simplest shape would be a triangle. And in this case, we could think of it as being bounded by a function in one case. Actually, we could think of these two boundaries as the graphs y equals c, which is a horizontal line, and y equals d, which is another horizontal line. In this case, the boundaries of this triangle-shaped region, the values of x would be between 0 and 3, but the values of y we could think of as being between the two functions, y equals 0 and y equals 2x. And so it's always below y equals 2x and above y equals 0. So the question is, how do we calculate the volume, say underneath this shape, underneath this surface, but lying above something like this? Well, the key idea is there's no rule that says that the inequalities for x and y can only hold numbers. We can also have variables in the bounds. Right? Looking at this diagram right here, for each value of x between 0 and 3, the values of y are going to range between the different values defined by this region. Specifically between the functions y equals 0 and y equals 2x. So for example, for x equals 1, the points in this region correspond to the y values between 0 and 2. Right, this set of values. When x equals 2, the set of points in this region have y values that range between 0 and 4. Right, because at 2, y equals 4. When x equals 3, the set of points in this region range between 0 and 6. Right? For any value of x, including all the in-between values, even when x equals 0, right, for each value of x between 0 and 3, y is going to range between 0 and 2x. Right, so in this case, we're going to write our double integral, and we can have variables within the inner bounds. And so in this case, this is why from now on I'm always going to put y as the inner variable, right? Because if I don't want to have a variable on the outside bounds, right? Because I want this to reduce to a single number. And that won't happen if I'm evaluating at a function out here. So here, the bounds are from y equals 0 to y equals 2x. And the result of this calculation, calculating this inner integral, is still going to be a function involving only x. So we're still going to be able to progress with our calculations just like we did with numbers. So let's see how this works out. Right, here's a sample function. Z equals f of xy. It's equal to 4 times x plus 6 times y plus 8. Let's say we want the volume under this region, but lying above the triangular region in the xy plane, defined by those equations we saw on the previous slide. So x ranges from 0 to 3, while y ranges between the functions from 0 to 2x. So we set up the double integral, and we first focus our attention on this inner integral. Integrating with respect to y is a variable, x is a constant. The antiderivative of 4x is a constant, so that antiderivative is 4x times y. The antiderivative of 6y is 6y squared over 2, which simplifies to 3y squared. And the antiderivative of 8 is 8 times y. We want to evaluate this from y equals 2x to y equals 0. So first, we plug in 2x every time we see a y. And so we're going to get 8x squared plus 12x squared plus 16x. Minus, we'll plug in 0 everywhere here. Well, those terms all become 0. And so when we combine like terms, we're left with a function 20x squared plus 16x. And then again, you have a single variable calculus problem. Right? We want to calculate this integral. So we need the antiderivative of this function. The antiderivative of 20x squared is 20 over 3x cubed. The antiderivative of x squared is 8x. Then we want to evaluate that between the bounds on the integral. So from x equals 3 to x equals 0. So we plug in 3 for the values of x, minus, we'll plug in zeros for the values of x. I love plugging in zeros. And then, when you're done, you'll get the number 252. Right? So that's the volume, the signed volume, underneath this surface above a triangular region. So, as long as you can write down the functions which define your region, you can calculate lots of new kinds of double integrals. So for this next example, let's say we want the volume under the surface 6xy plus 2. Lying under this surface, but over this shaped region. So this is actually, oops, it's not a parallelogram. It's a trapezoid. I hope you'll forgive me that. You can ignore that comment. So over this region, this is actually a trapezoid shape, right? And in this case, the boundaries are x equals 1 and x equals 2. The y boundaries are the functions y equals x and y equals negative x plus 6. And so that forms the boundaries of this trapezoid shape. And so here, x goes from 1 to 2. When calculating the y bounds, sometimes you have to look at the graph to figure out which one goes on the bottom. So for this part of the graph, right, over here, y equals x is on the top. But in the region we're interested in, y equals x is on the bottom. Right? So this next inequality goes, y goes from y equals x up to y equals negative x plus 6. And so now we have to solve this double integral. And this one's a little bit trickier because we have functions of x for both bounds on the inside, but the function we're integrating is a little bit simpler. So let's go ahead and calculate the antiderivative of 6xy plus 2 with respect to y. And that antiderivative turns out to be 3xy squared plus 2y. We need to evaluate that from y equals minus x plus 6. So we'll plug that in for y. Minus y equals x. So we plug in x for y. Then we're going to have to distribute this through and expand all these terms. Right, so for instance, squaring negative x plus 6 gives us this. We have to distribute through. And when you're finally done combining like terms, I think you'll find negative 36x squared plus 104x minus 12. Right, this is the function we want to integrate next. Then we integrate that from 1 to 2. The antiderivative, again, just uses the power rule, increasing the exponents by 1, dividing by your new exponents, and then evaluate that from x equals 2 to x equals 1. So plug 2 in for x, minus plug 1 in for each x. And when you simplify, I think you'll find that the volume turns out to be 60. Right, so you can do all sorts of different shapes. Here's an example of the base where the lines, well, the boundaries are not all lines. In this case, one of the boundaries is a curve. In this case, we're looking for the volume underneath the same function, but lying over a different surface in the xy plane. Specifically, I'm interested in this region from x equals 0 to x equals 1 between the curves y equals x and y equals x squared. Right, so in this case, our boundary conditions, x goes from 0 to 1. Then for each of these values, you have to figure out what goes on the bottom and what goes on the top. It might seem that x should be smaller than x squared. It might seem that we should say x less than y less than x squared. But in the range between 0 and 1, x squared actually turns out to be smaller. So this next set of bounds is x squared less than or equal to y less than or equal to x. We then set up the double integral we need to solve to calculate this volume. The function being integrated. As always, we're going to do dy first from x squared to x, the y, and then the x goes from 0 to 1. The antiderivative of this function is the same as last time, so it's the same function as last time. 3x squared plus 2y, integrating from y equals x to y equals x squared. So first we plug in an x for y, minus, we then plug in x squared for y. And then, there's really no like terms to gather in this case. So we just have to integrate this entire function from 0 to 1. And so once again, we use the power rule. Right, that leads us to a number of fractions in this case. But then we're evaluating it from x equals 1 to x equals 0. X equals 0 is my favorite number to plug in. X equals 1 is a close second. So plugging in 1 for all these x's, minus plugging in 0, well, that just gives you 0. I didn't write down minus 0 this time. Probably the easiest way to do this is give everything a common denominator, and you'll find that the volume in this case is 7/12. All right, so there we go. There's another example of a volume problem. We'll do one more. You might think, well, we're going back to straight lines. This is going to be easy. But this one is surprisingly a little bit tricky. You might notice there's 3 functions of y in here. But the last time we did a triangle, there were only 2. What gives? And it has to do with the way this triangle is oriented. And so we're going to look for the volume underneath this function, x plus 2y plus 3. Overall, the values of x go between 1 and 3. But on the left half of this triangle, between x equals 1 and x equals 2, right, the y values range from y equals 0 on the bottom to y equals x minus 1 on the top. So for this range of values, y goes between these two bounds. Then, on the right part of this triangle, between x equals 2 and x equals 3, the y values range from y equals 0 on the bottom to this other function, y equals negative x plus 3. And that's on the top for this part of the triangle. So again, for these different x bounds, you have some different y bounds, which means to solve this problem, you need to solve it in two parts. So now you get to do two double integrals. That's 4 times as much fun as an integral problem from single variable calculus. Right, we're integrating the same function in each case, and that'll be useful because we'll have the same antiderivative, but the bounds are different. Right, in this case, I have the bounds of the left-hand triangle, x from 1 to 2, y from 0 to x minus 1. On the second double integral, right, we're looking at the bounds for the second part, the right part of this region. X ranges from 2 to 3, while y ranges from 0 to minus x plus 3. But mechanically, the steps are the same as what we've done before. Right, in both cases, you calculate the antiderivative, and then you evaluate at the given values of y. And then when you're done, you'll have a function in each case. Because you have different functions of y, however, you're going to get two different functions once you simplify. So I've left out some of the intermediate algebra steps, but pretty sure this is what you're going to get for each function. And then it turns into two regular old single variable calculus problems. Right, find the antiderivative of 2x squared minus 2. Evaluate it from x equals 2 to x equals 1. Find the antiderivative of minus 6x plus 18. Then evaluate it from x equals 3 to x equals 2. Let's put a dot, dot, dot here. You're going to get a number at the end. The important part is just this process works a little bit differently because it's a two-part problem. Twice as much fun. All right, and now it's time to learn math by doing math. So I'd like you to try your hand at finding the volume underneath the curve z equals f of xy. This is going to be 3x plus 2y plus 1 that lies over this region. And so in this case, this part, the bottom of this shape is y equals 0. The top part of the shape is y equals 1 minus x squared. And the x boundaries, well, they occur when the two curves intersect. That's at x equals negative 1 and x equals 1. So go ahead, set up this double integral and solve it, and you'll get a number out which represents the signed volume of this surface. And always remember too, it is a signed volume, so sometimes you like cancellation between negative and positive parts. That's okay. But that is how you calculate double integrals over non-rectangular bases. There is still the special case of circular bases, which can be a little bit confusing, so we'll save that for the next video. This is a good breaking point for now. Thanks for watching.